In this video, we will learn what a chemical salt is, look at how they are named, and describe the preparation of soluble and insoluble salts. We will also examine why we consider certain salts acidic, neutral, or basic. A salt is a type of chemical compound. The International Union of Pure and Applied Chemistry, IUPAC, considers any chemical consisting of an assembly of cations and anions to be a salt. Cations are positively charged ions and anions are negatively charged ions. So, for some people, any ionic compound is a salt, and all salts are ionic compounds. Practically speaking, when we refer to salts, we often refer to those specific ionic compounds that can be produced by the reaction of an acid and a base. In this case, we're only considering the type of acid with H+ ions that can be donated. These are Bronsted-Lowry acids. You may see this reaction. An acid plus a base reacts to form salt plus water. This equation only really applies when we're dealing with a base with OH- ions. This is otherwise known as an alkali or an Arrhenius base. However, a lot of the bases you're likely to come across fit into this category. We know generally a salt is a combination of cations and anions. And the chemical symbol for water is H2O. But does the cation or anion come from the acid or the base? Well, if we start with the base, we know in this case it has to have OH- ions, which means it must be paired with a cation. And the acid containing H+ ions contributes the anion. So here we have the general formation of a salt from an acid and a base, and H2O, water, is formed by the reaction of H+ and OH- ions. Let's start with some of the acids you might be familiar with and see which anions they contribute to a salt. Hydrochloric acid, HCl, will react with many different bases. Whatever the base is, the reaction will always produce a chloride salt, a salt that contains chloride ions, Cl-. Sulfuric acid, H2SO4, will generally react with bases to produce sulfate salts, salts containing SO4 2- ions. Nitric acid, HNO3, will produce nitrate salts, salts containing NO3- ions, and hydrobromic acid will react like hydrochloric acid, but instead producing bromide salts. So we should be able to apply this to any acid. Now let's have a look at a few example bases. Sodium hydroxide, a common base, has the formula NaOH. When sodium hydroxide reacts with an acid, it produces a sodium salt containing the Na+ cation. When potassium hydroxide, KOH, reacts with acids, we produce potassium salts containing K+ ions. And we see a similar behaviour for ammonium hydroxide, NH4OH. Ammonium hydroxide reacts with acid to produce the ammonium ion, NH4+, and ammonium salts. The majority of salts are metal salts because they're derived from metallic elements, but there are non-metal salts like ammonium salts which are derived from non-metals. Now let's put these two components together and see which salts we can make. Acid plus base react to form salt plus water. If we react together, hydrochloric acid and sodium hydroxide, the salt formed will be made up of anions from the hydrochloric acid, meaning we're getting chloride anions. And our cations, Na+ or sodium ions, come from the base, sodium hydroxide. We can write the formula HCl plus NaOH react to form NaCl plus H2O. So what about some other acids and bases? What do we get if we react sulfuric acid and potassium hydroxide? The acid contributes the sulfate anion and the base contributes the potassium cation, giving us potassium sulfate. We can convert the word equation to the symbol equation, and since sulfuric acid is diprotic, it has 2 hydrogen ions rather than 1, we need 2 KOH in order to balance, producing 1 K2SO4 plus 2 H2O. Next we have nitric acid and magnesium hydroxide, which react to produce magnesium nitrate. And here are the chemical formulas. Look out for magnesium, which has a charge of 2+, meaning we have 2 OH- ions. This means we need twice as much nitric acid as we have magnesium hydroxide in order to balance the equation. You could even take a good guess at what would happen if you took phosphoric acid and ammonium hydroxide. Phosphoric acid produces the phosphate anion, so we get ammonium phosphate. This one's a little bit more tricky, so I'm just going to give you the balanced equation and move on. From the last section, we saw a lot of names of salts. How would we go about naming a salt that we've never heard of? This is the formula of a salt, HgS. Hg is the symbol for the element mercury, and S is the symbol for the element sulfur. Mercury is a metallic element, and sulfur is a non-metallic element. We can remember this from the position of these elements on the periodic table. To the left of this zigzag line, we tend to find metals, and to the right, we find non-metals. Therefore, we expect HgS to be an ionic compound. Metals tend to lose electrons more easily than non-metals, so we'd expect the metal, mercury, to contribute the cations, and the non-metal, sulfur, to contribute the anions. Sulfur, like oxygen, is in group 16, otherwise known as group 6, of the periodic table. We would therefore anticipate that atoms of sulfur would gain 2 electrons each to form S2- ions. Since in the formula mercury and sulfur are in a ratio of 1 to 1, we must have Hg2+ ions as well. When we name ionic compounds like salts, we always put the name of the cation first and then the name of the anion. The name of a metal cation is the same as the name of the metal, so mercury to mercury. But the name of the anion is different. In this case, we have sulfur transforming into sulfide. Ide indicates we're dealing with an anion that's monatomic, a single nucleus. And for reference, the suffix ate or ate has a slightly more complicated meaning, but it always means we're dealing with a polyatomic ion containing oxygen and one other element. In this case, however, our final name is mercury sulfide. Mercury, however, does display multiple oxidation states sometimes, so we could be extra precise and write the name of mercury sulfide as mercury 2-sulfide. However, for elements in the main group, we generally won't need to do this. We can easily tell the name of a salt from other chemical names in these ways. There will always be at least 2 distinct terms, one for the cation and one for the anion. They also, generally speaking, won't use prefixes like mono, di, and tri. So for instance, magnesium chloride, MgCl2, would not be called magnesium dichloride. But you will see at the end of the name for the anion suffixes like ide, ate, and ite. Ate and ite both describe different polyatomic anions containing an element and some oxygen. But we don't need to go into the distinctions in this video. So we've looked at breaking down salts into metallic and non-metallic salts, but there's another property which is solubility that's often used to categorize salts. You might hear about a salt being either soluble or insoluble. But this is a rough grouping, and solubility is a continuous spectrum, going from completely insoluble all the way to completely soluble, which is what we call miscible. 2 miscible substances will form a solution no matter what ratio they are in. One of the most common ways we assess solubility is by seeing how much mass we can dissolve in a given volume of liquid. In this case, we're looking at the number of grams of substance we can dissolve in 100 ml of pure water. We call the solution with as much substance as we can ordinarily dissolve a saturated solution. Because of the range of solubilities in these examples, I'm going to have to use a log scale, where each increment indicates multiplying or dividing by 10. Our favourite salt, sodium chloride, comes in at about 36 grams per 100 millilitres at 20 degrees Celsius. And similar metal chlorides come in with similar solubilities, with magnesium chloride and aluminum chloride being a little higher. And toward the other end of the spectrum, we have a substance we generally consider insoluble, which is calcium carbonate. Depending on the form, it has a solubility around 7 times 10 to the negative 4 grams per 100 ml of water. However, there are substances even less soluble than this. On this metric, silver iodide is about 40,000 times less soluble than calcium carbonate. Silver bromide isn't much better, and even silver chloride doesn't make it over the hill. But comparatively speaking, silver fluoride is incredibly soluble at 172 grams per 100 millilitres. So all we can be sure of is that as we move to the right, the substances are more soluble, and as we move to the left, they are more insoluble. But what tends to happen is that anything below a certain threshold is just called insoluble, and anything above is just called soluble. The position of the boundary doesn't need to be actually clear, because there's such a big difference between the common salts we call soluble and the common salts we call insoluble. So for the next bit, just bear in mind the rough difference between insoluble and soluble. What we are going to look at next is how to synthesize some of these salts practically. If a salt is insoluble or poorly soluble, we can sometimes synthesize it using a precipitation reaction. A precipitation reaction is simply a reaction when a solid is produced from a solution. In a precipitation reaction, we typically see one or more dissolved solutes, reactants, produce at least one solid product. In the lab, you'll typically see these performed by the mixing of two different aqueous solutions. Chemicals in the two solutions will react and form a very fine powder of solid product. These particles will either stick around, floating around in solution, forming what we call a suspension, or the particles will quickly clump together and fall to the bottom of the container, forming a precipitate. For some suspensions, it may just take a great deal of time in order for the solid to collect at the bottom. Whether the solid collects or not, the next step is the same. The mixture is stirred up, and the whole collection is filtered, leaving the solid in the filter paper, which can be washed with more solvent, dried, and left pure. We can demonstrate this whole process using lead nitrate and potassium iodide solutions. Both of these solutions are colourless. When the two solutions mix, potassium iodide quickly forms. It's an insoluble, shiny yellow solid. These characteristics give the general experiment its name, the Golden Rain experiment. After filtration, washing and drying, we end up with pure lead iodide. But filtration on its own will not work if the salt is soluble. If the salt is soluble, it won't be easy to separate from the rest of the solution, which will have potentially other products and leftover reactants. The first scenario is when we are making a salt from an acid and a base, and the acid and the base are both soluble. If we're dealing with our simple acids and bases, we're going to produce salt and water, which is fine. But we really don't want any of the acid or base left over at the end. The easiest way to guarantee at least a relatively pure product is to use exactly the right amount of acid and base. Let's have a look at a scenario where we're making barium chloride, the salt, from hydrochloric acid and barium hydroxide. And this is what we get when we convert the names into the chemical formulas. But we need to balance by adding 2 HCl per BaOH2. So let's imagine we're mixing together 1 molar solutions of each reactant. In order to get twice as much HCl reacting with barium hydroxide, we'd need to have double the volume of our 1 molar HCl solution. So we'd mix the solutions in a ratio of 2 to 1. This would get us our final solution of barium chloride in a relatively pure form. And then we could remove the solvent, the water, by evaporating it off in an evaporation dish. If at the beginning we'd measured exactly the right amounts of hydrochloric acid and barium hydroxide, we'd end up with pure barium chloride. Now the last scenario we're going to look at is when we synthesize a soluble salt using a soluble acid and an insoluble base. Since we can remove solids easily by filtration, all we need to do to get a pure product is add an excess of the solid base so we use up all the acid. We'd add the solid base to the acid solution, make sure we had an excess and that all the acid was reacting, giving it a good stir just to make sure. This would give us our pure salt solution with some base we just need to filter off. At the end of filtration, we'd have our pure solution in a flask, and after evaporation, we'd have our pure dry salt. Now before we finish, there's one more topic about salts we need to address. And that is that salts themselves can be acidic, neutral, or basic. Acidic salts produce acidic solutions and react with bases. Basic salts produce basic solutions and react with acids. Neutral salts produce neutral solutions and don't react either with acids or bases. So neutral salts produce solutions with pH about 7, acidic salts produce solutions with pH less than 7, and basic salts produce solutions with pH greater than 7. One of the most well-known acidic cations is ammonium, NH4. But most cations in salts are neutral, particularly the metal salts. Basic anions include carbonate, CO3 2-, and hydrogen carbonate, HCO3-, fluoride, F-, and you can even consider oxide ions basic because oxides tend to react with acids. The group of neutral anions includes the other halides, chloride, bromide and iodide, nitrate, NO3-, and sulfate, SO4 2-, although there are arguments to be made that SO4 2- is slightly basic. When we do an acid-base reaction that produces a salt, we can look at the strength of the acid or base to see what type of salt we're likely to produce. A strong acid and a strong base will produce a neutral salt. A strong acid and a weak base will produce an acidic salt. A weak acid and a strong base will produce a basic salt, and a weak acid and weak base will produce generally a neutral salt, although it can depend. So to sum up, a salt is made of cations and anions and can be made by an acid-base reaction. The acid provides the anion and the base provides the cation. Salts are made in different ways depending on their water solubility and the solubility of the acid and base. Salts can be acidic, neutral or basic. Strong acids react to produce neutral anions, and weak acids react to produce basic anions. And strong bases produce neutral cations, and weak bases produce acidic cations.